Hi, everyone. I am not Adam Jacobs or Brian Cantrell. I appreciate you showing up for my talk in spite of that. So let's get started, I guess. As mentioned, I work at OmniTI. My main role there is I lead the database operations team. We deal with what is normally known as sort of, whoa, hey, back up. New MacBook Air, don't buy one. So we deal with sort of high-level database work, high transactions, large-scale databases, terabyte-plus type stuff, mission-critical infrastructure, basically like very, very important systems, right, that people rely on for their businesses to actually work. We do a lot of Postgres-related work. We're actually kind of polyglot about our database philosophy. So we deal with a number of different databases, some that we like and some that we don't, like SQL Server. But mostly we tend to deal with Postgres, and I think we're probably most known for working on Postgres. And the talk today is kind of going to be about Postgres and how it's failed us and how we tried to get around that and dealing with that problem. But I think that's pretty transferable between all different vendors or community projects in either case. So why Postgres for scalability? I thought I needed this slide, really maybe more than I actually do need this slide. I've seen a lot of talks today that have mentioned that people are using Postgres all over the place. So all the basic reasons that you might think of using Postgres, that's why we picked that one for scalability. You can, of course, make any technology work. We find this one to be pretty much the easiest one. So the main problem that we're going to speak about today when it comes to running Postgres in sort of large-scale environments is known as the bloat problem, right? And the bloat problem is basically the idea that your data footprint, right, becomes very critical for your performance. And so you want to try to keep that very low, right? Size on disk is going to affect the amount of RAM you need, disk speed that you have, your storage requirements, that kind of thing. And bloat is sort of the unused disk space that creeps up into databases, right? And what I mean by unused is more it's wasted space. It's not needed for actually storing your data or managing the data inside the system. And so you'd sort of think about that and say, like, well, why is there bloat? That doesn't really make a lot of sense. Like, what are you talking about? And how do you get bloat or this seems like a bad idea to have this in your database. And it is, but the reason for bloat goes back to the way that Postgres does its Mvcc. For those, everybody know what Mvcc is? I'm going to attempt to distill a very nice talk that Bruce Momjian does in 90 minutes into about 6 slides that will explain it. But the basic idea is to use multiple versions of data inside the database in order to allow readers and writers to work concurrently without blocking each other, right? And this isn't anything common to Postgres, right? Everybody more or less has something like this. Oracle implements it, MySQL implements it, Informix, like on down the line. Mvcc is pretty common. Now, a lot of them do it in different ways. There's not just one way you can implement this, right? The idea can be implemented different ways. So really, and when you do this, you end up with sort of dead space as a result of that work. So it's not really even a problem about Mvcc. It's really more of a problem of non-overriding storage, right? If you use something like MongoDB, you actually have to deal with bloat as well, right? If you read through the MongoDB docs, they'll talk about if you need to shrink the size of your data files, either doing a dump of all your Mongo data and put it into a new instance. There's like the MongoDB, the repair command that you can run, which tries to compact all your data. They've gotten this to be simpler to do. There's now an internal command to the database you can run, also compacts data inside the database, right? And that's because it has non-overriding storage. There's other systems that have this as well. It's not even like in a traditional database sense, right? Like Lucene has the same problem. CouchDB, if you use that, it has views. The views end up doing non-overriding storage, so you end up having to compact those. So any system that you have, and as you watch new systems come out, it's been sort of interesting to watch with a lot of these NoSQL databases that have come out recently. One of the first things I always look for is like how do they do their storage and how they do their updates, right? And if it's non-overriding storage, you know that system is going to have a bloat problem at some point, right? And so if they're going to have a bloat problem, how are they going to deal with that? How are they going to clean that up? So you can watch for that in any database, and it's a good sort of evaluator of the maturity of the system, right? If they don't have a solution for that, or what is usually the common solution, the first one that Mongo did was, hey, dump your data and restore it into a new system, right? To me, we've definitely got an immature system if that's your only option. Probably not one you're going to try to scale with either. So anyways, getting back to bloat, it's an aspect of non-overwriting storage that you end up having to deal with. So before I get into sort of our travails with it, I do want to dive a little deeper into the Postgres Mvcc architecture because it makes a little more sense as we're going through this to understand how this stuff works. So boiling it down into very simple terms, but pretending to be technical, Postgres maintains global transaction counters, right? All the different backends that are connected and transactions that are running, Postgres is keeping track of who's doing what and has these transaction counters inside of it. When it stores data on disk, it's mainly keeping track of two things, which are when the data was, which transaction created that data, and then ultimately which transaction would mark it as no longer available, right? Being either an update or a delete statement. So it keeps track of those two things, and then using those counters for each row of data, right, it can look at an individual session's transaction ID and determine whether it should be able to see that row or not, right? The goal there really is the sense that a transaction that's reading data can look at data that's there, and if somebody else wants to go and update or delete that data at the same time, they can work on a different version of the data and still be able to work through their, work on data at the same time. So what that looks like on disk, right? If you do an insert, this is sort of an example where, so maybe my data is the user ID, right, of X42. We do a create, and we put in like a transaction counter, right? And then there's a little space left there for the expire row, and that's what a row looks like on disk. Now, I'm glossing over a whole bunch of other sort of internal counters, so if you know the Postgres storage format, sort of let that slide by. But these are the main ones when it comes to the Mvcc stuff. So then if you do a delete, basically Postgres just needs to go in and put a marker and say, hey, after transaction 38, nobody should be able to see this row, right? Makes sense. When you look at an update, the process within Postgres basically is just doing these same things, right? So you would take, say we had a row, user X69, created on transaction 43. When you go in to update him, right, we just put a marker in for the expired row 56, right? And so now you have both an old and a new version, though, that are available on disk. And that's sort of the thing to keep in mind, right? That one of these rows will be a dead row, and it's the old row that's now been marked expired, and then there'll be a new version of that row that gets created with the updated data values. Yes, I was noticing that. So for those that are wondering, if you look at this, these are actually kind of backwards, right? The dead row should be marked as expired, and the new row should have sort of the open spot in it, right? So anyway, so you can use that and figure out who should be able to see this. But the bloat problem comes in that we have this sort of row on disk that nobody can see, but it is actually still sitting there on disk, right? So that's the bloat. That's this data that we don't need anymore. And the tricky part is that at the time you delete the data, you probably actually need to leave it there on disk so somebody who's still going on in the system can see it, right? Otherwise, you'd have to wait for all transactions to sort of say, I don't need that data anymore. Then you could mark it as deleted. Then you got locking issues, right? So we're trying to get past that. And so clearly, you could look at this and say, this is going to be a problem over time. In old Postgres, like way back when, there was this concept called time travel, right? And the idea was if we just leave all these rows on disk, like this will make it really awesome to be able to go back and look at versions of our data. And that does actually sound really awesome, but if you think about the amount of disk space it would take to keep every version of every row of your data, for most people doing like OLTP type work, it's just not practical, right? So Postgres has gone about coming up with ways to solve this problem. The two biggest things that Postgres will do internally for you is it has like two different methods. One of those methods is known as, sorry about that. One of those methods is this thing called heap-only tuples, right, which is sort of an on-the-fly update. If you're familiar with, hold on a second. If you're familiar with Oracle or InnoDB and how it deals with bloat, it sort of does things on the fly as well, right? So in those systems, when you write a record, it takes the old record, puts it off to the side, and then puts your new record in its place, right? And so its bloat is this sort of side piece of information of all these old rows. It eventually has to clean that stuff up. In Postgres land, we just do it right in the same table. The data shows up right alongside of the old data, new data right there together. And so it can be cleaned up on the fly in some cases, and that's what the hot does. Does it for updates, and can't do it for deletes necessarily, but for update chains it can do it. The one problem is that hot actually doesn't work when you're updating index data, right? If the index value is actually changed, so if you have like a index on a timestamp column and you update the index value, hot can't clean it up within the table itself. In Postgres, index values, and all the index values are stored in a separate file, right? So it has to go and actually update that value. So it really needs a second sort of cleanup piece to go on. The other way, and probably the one that most people are really familiar with, hot is sort of like an internal thing. It just kind of happens. It's been there since 8.3, so I mean it's pretty tried and true, I guess, at this point. Hopefully none of you are running older than 8.3. But that one's sort of happening on its own, and you don't have to deal with that much. The one most people are really familiar with are vacuums, right? Everyone, if you've run Postgres, you know about the vacuum command. It's sort of almost an inside joke, I guess, for other folks that look at Postgres and know that you have to have this vacuum thing, right? And vacuum is sort of this bulk processor that comes along and examines all the rows in your table and says, like, oh, these ones are no longer needed, right? I can mark these to be reused. And that will free up space for later transactions to write data into. And so vacuum works pretty well, but it doesn't work as well as you would hope. Part of the problem with the vacuum system, you've got to actually wait for all transactions to complete. If I go and I update a row and I commit that, but there's some other query that's in the system that's long-running query, even if I were to go try to vacuum it, well, the other query might actually still be looking at the old version of the row. So you sort of have to play off the fact that you have multiple transactions going on, which means that the vacuum process is going to have to wait for everybody to finish, right? Another problem with the vacuum method is it can't remove any pages within a file. Yep. The vacuum process? Yeah, so it does know that, but the problem is if you run a vacuum soon enough, there could be a query that still needs to look at that row. So it would look at that row on disk, the old row, and say, oh, there's this guy who still needs to see it. Right, so it just sort of leaves it there, yeah, because it's kosher and it can't mark it to be reused because the other guy can still see it, right? So when it tries to do its cleanup, though, one of the things it also tries to do is look for any pages inside of the table file that are completely marked as either reusable or no longer, no one can see that. And if it can find those, it can actually free that space up, and you can actually get disk recovery. And a common sort of mistake that people think of with vacuum is they think, well, if I run vacuum on my table, sometimes they see it recover a little bit of disk space, sort of verifying with DF, but not all the time. And in most cases, it probably can't really recover disk space, right? It can set sort of what is, in old terms, I think was called like the high water mark, right? Whereas if you do a bulk update and you double the size of your table, it will do this vacuum. It will try to clean up some of that, but a lot of that stuff it just can't remove, right? Your table won't grow any larger, but it doesn't reclaim that space. If you try to put in more data, it won't need more space because it has all this sort of reusable space from old transactions. But it's not going to necessarily shrink it down. And the big part of that is, a large number of transactions going on make that harder. It has to be able to get just, at least some level of locking to make that work. And there's sort of other internal issues going on with that. So that's another sort of problem of the vacuum process. Of course, the other sort of obvious thing is it costs a lot of I/O to do vacuums. This has actually been really improved in recent releases. I think 8.4 was probably a good marker. If you're having a lot of vacuum issues with I/O, then 8.4, get on something newer than that, and you should be better off. But still, you've got to do a lot of extra scanning. And the good thing is, and the philosophy behind the way Postgres tries to deal with this is, if you do this in vacuum, right, it's sort of an out-of-band process. It doesn't affect your actual transactions. So when you're trying to do the inserts and updates and selects, that actually power your application, you're not slowed down by having to do the disk cleanup, right? We do that in a separate process that doesn't bother that. But it does lead to extra I/O activity. So there's a trade-off that's being made there, right? And because of that, vacuum does a pretty good job. And I would say if you're running a new system, probably you don't have too many problems. But occasionally there are definitely workloads where you'll see bloat start to creep into things. And so, sort of looking at Postgres has been around for a long time. People have been having these issues for a long time. They've been trying to improve the process. They still have sort of the more rudimentary options on how to clean up data, right? One of those is with the vacuum command that most people are familiar with. There's a version of that called vacuum full, right, which is pretty common, which is similar to another command that Postgres has called cluster. And the good on these two particular commands are it actually reclaims all of this dead space, right? It will actually go and it will shrink your data down and make it take as small amount of space as possible on disk, right? The problem with those solutions are, though, like the biggest one is they need an exclusive lock on the table, right? So nobody else can be reading or writing. And what that gives, the Postgres process, the advantage it gives it is that when you do this vacuum full, it knows, hey, nobody else is looking at this data. I have an exclusive lock on the table. There can't be anybody else doing anything. So now I can go and I can shuffle data around as much as possible to try to clean things up. Bad sides also, though, right, I mean, you're rewriting all the data in your table. This is better than, somebody telling you dump your data out and restore it. But on the other hand, it's still, pretty heavy, right? There's pretty heavy I/O that's going on. You also, of course, need a lot of space. If you're going to rewrite your table data, you need space to do the extra writes before you can free the old data. And a lot of times we've seen people get bitten by this where if you're running out of space and you realize that you have a lot of bloat, one of the problems is you probably, it's quite often you don't have enough space to actually do the vacuum full to clean up the bloat to now not have space problems, right? It's like sort of circular issue there. So it's good for cleaning stuff up if you can actually do it. In large-scale systems, though, the option to run vacuum fulls or clusters basically goes out the window for anyone doing continuous 24/7 operations. So that's sort of one, it's a heavy-handed approach and doesn't work in the cases that we work in a lot, I guess is also worth saying. The other part of dealing with bloat in Postgres is not just in the tables, right? There's also issues with bloat in the indexes. And Postgres gives a reindex command, which basically just rebuilds an index, right? And a lot of systems will have something similar to this. This will recover any bloat that you see in the index. The one thing, though, is it requires an exclusive lock on the index itself, right? So that won't necessarily block people from, looking at data in the table, depending on if they need to use that index. And this is one where this used to be a problem. Now there's a pretty good workaround that most people in sort of these high transaction OLTP systems are using, where if you have an index that's really bloated, you just create a new index on the same column, right, concurrently, which allows it to sort of build it online. And then now you have two indexes on it, but once the new one's in place, that one gets favored by the optimizer, and all the queries start looking at that one, and you can get rid of the old one, right? So again, you still need extra space in order to build this, but at least you don't disrupt operations. And that's sort of, our critical goal in most of these systems are, we'll run the database and do whatever we have to do, but we can't actually disrupt operations, right? We can't take anything down. And so that's sort of a big component. Sadly, reindexing only works for index bloat, though, right? The create index concurrently to sort of clean that up. You can only do that on indexes. Postgres doesn't have an online table rebuild. So while you're happy with doing it on the indexes, even if you're cleaning indexes up regularly, eventually, like, the table problem is still going to come and bite you. So one of the first things that we really needed to wrap our head around was figuring out, is this actually a problem, or how much of a problem is it for us? And the way that we did that, we sort of, we being, I guess, Postgres community, developed two main tools to do this. The first one is this script called check Postgres. It's basically just a Nagios plugin script. Has like 50 different things that you can monitor in a Postgres database and integrates with Nagios and a couple of graphing tools and that kind of thing. And basically the way that it works, though, is it looks at the structure of your table, computes what those data values, the size of those data values should be on an estimate basis. And then if the actual size differs too much from that, right, it throws a Nagios alert and tells you got a problem with bloat. That's all well and good, and actually that was the sort of the first system that we were really using regularly was doing that. But what I sort of found was, operationally speaking, we're a big proponent of having sort of actionable alerts, and with these sort of bloat alerts, a lot of times you'll get them and they'll wake you up at 3 in the morning and you're like, that's great, but I can't do anything anyways. So it's good to know that I have this problem. It's not good to wake me up. And even if, like, even if it woke me up and I could do something, I probably wouldn't at 3 in the morning. I'd just wait until, when I get to the office. Because bloat usually isn't like that critical of a problem, right? That it can't wait a few hours till somebody gets, into the office and actually has coffee. So it was still a good script, and we still use that in a few places. But what we ended up doing was we wrote another tool, which was the Bloat Report, which is basically just a simple script that looks through all your tables, does this same calculation of how big do we think these tables ought to be, right? And then how big are they actually looking at the size on disk? And then we spit out, sort of all those statistics of, here's how big it is, here's how big we think it should be. You're wasting, 2x the space that you ought to have for this table. And then that works for tables or indexes. And, you can get a report of your system and see sort of how healthy it is from a bloat perspective. And part of the problem with this is that Postgres doesn't really give you good tools to figure out how bloated the system is, right? It's a known problem within the system, but it's sort of that first step where you see that the vendor has put something out, there is a problem, but they don't give you really a good way to track it or a good way to deal with it, right? They give you some tools to do that, but how do you even know that you have bloat? Most people don't even know that. These scripts have been created, they've been around now for, let's say, 2 or 3 years, right? But I've been working with Postgres for, at least 10 years or more now. And I can remember 10 years ago, people would say, my query is slow. And one of the things that people would say, like, they'd say run, explain, analyze. But one of the other things they would say right away is make sure you vacuum your table before you run this query, right? Because they were sort of with the knowledge that, hey, it's a good chance that your tables are bloated, and that's one of your problems. So clean that stuff up, and then your queries will be faster, right? Which, it's not that was bad advice, but it always seemed like, we're missing something and that we don't know that our tables are bloated ahead of time. We haven't automated that. We haven't regulated that, right? You're a DBA, and you figure this out because your queries have suddenly gotten too slow. And so the goal is, like, how do we be more proactive about that stuff, right? And that's where these kind of tools start to come into place. And so these are pretty good for that. And if you look in any database system, like, sort of look at those guys sort of pushing around the edges, part of it, I think, is you got to have the right philosophy, right? The philosophy that says, even if the vendor is sort of letting me down, if I have a known problem, let me go in and look into the system, what is exposed, and let me build something to track that, and then I'll build something to deal with it, right? Most of these row size estimates that we're getting, there's documentation on how large should an integer field be, right? So you multiply that times the number of integers, then you look how big it is on disk. This isn't necessarily that hard, but you do have to sort of figure out the pieces of what can I see, and how does that get me to what I want to actually be able to track. Okay, so we built these tools. Now we can tell when we have bloat and when it's a real problem. As a consulting company that doesn't want to make money, somebody comes to us and we don't recommend that you have a vacuum needed problem. We say run the bloat report, and then we can tell you for real if that's your problem. But in the cases where it actually is your problem, because bloat does exist and it's out there, we sort of had to try to figure out, well, how do we deal with this and how do we clean this up? If vacuum's not getting the job done and we can't do vacuum fulls and we can't do clusters, we need some other method to do this. Right? And so we came up with this idea, which ultimately not the best idea. But basically what we decided to do was we took this idea that if you vacuum a table, all your old rows that nobody can see anymore that are at the sort of the start of the table file will be marked as reusable. Right? So then if we go and we update all the rows towards the end of the file, they'll get rewritten into the old space. And then if we vacuum again, the rows on the end of the file will get removed from the list, right? Because now that's all clean and it can shrink that down. So we can use sort of this round robin of vacuuming and updating approach to shuffle the data within the table files on disk and compact the thing down. And because you're using SQL level tools, right, stuff that users and applications are supposed to be able to run, probably in a manner not really thought of as the right way to do it, but you're using it at the user level, so it's supported and it's okay. It doesn't block anything really. We could script that, and we did, and we sort of put that out there. And said this is one way you could clean up bloat without doing any really heavy locking, just enough to get the updates and do the vacuums, and this will get you what you want to do. So. We had that solution sort of designed and developed. We thought this could work pretty well, But as we started to really apply it into different scenarios, we found it didn't really kind of do what we wanted it to do. The first problem was it took a lot of time and it took a lot of I/O, especially in a busy system. When you're trying to do sort of these updates, that under the hood are shuffling data around in pages, your application is still running as well, and it wants to insert data and it wants to update data, and it actually, it doesn't care about these sort of under the hood things that you're trying to accomplish. And so it would take a long time to really compact data down in this way. It would work, but it was so intensive that you sort of felt like if I have to take 3 or 4 days of watching this because I'm doing all this work under the hood before I actually clean things up, I need a more efficient manner, right? I can't get enough stuff done if I'm spending all my time with this. So definitely a heavy concurrency. Another problem there is when you have these other transactions in the application going on, not only are they sort of getting in your way of the flow of data that you're trying to achieve, but oftentimes they can be bloating the table out faster than this thing could actually recover it, right? You have enough updates already going on that you're not making much headway in this case. And so the other problem with compact table is as you're doing these updates to the table data, it actually is bloating out the indexes on the other side, right? And originally when we wrote the tool, we sort of thought, well, that's okay because we have a way we can deal with that, right? We can always create a new index concurrently, it'll build online, and we'll drop the other one. So we sort of made that design trade-off and said, well, it is going to bloat the indexes out, but we can clean that up later. But you're sort of saying like, well, I mean, you're trading off one bloat, shifting it around to another part of the system that you then have to clean up. So again, it sort of came back to the idea of, how efficient is this tool, and is it actually doing what we want it to do? And so eventually we sort of said, compact table is not the thing. Let's keep looking. So we finally found a tool that we thought, hey, I think this one will actually work. And this was mostly digging around on the internet, watching mailing lists, looking for similar tools. And this one popped up on the radar called PG Reorg, right? And it's starting to get a lot more notice because it's solving sort of a critical problem that isn't addressed anywhere really well. The PG Reorg tool, though, it's basically supposed to be like a vacuum or cluster replacement. And it's a command line tool that you run, and then it goes and works on your database. And the goal is, in sort of the Oracle sense, to do an online table rewrite, right? So it can rewrite all the data in your table, doing it without blocking transactions, and then clean things up afterwards. It uses a little bit of locking in order to accomplish this, but it's pretty minimal. If you can ever get alter tables or drop indexes to work, then you can probably get PG Reorg to work. For those that aren't familiar, it's developed by NTT. This was a nice thing about it. NTT has been working with Postgres for, I don't know, a long time, half a dozen years or more. I've met several of the guys who do work for them, and I know the environments that they're working in. And so it wasn't just some guy wrote a script. It was somebody who has been working with Postgres who we had some confidence in. It's BSD licensed, which is always a bonus, and it's written in C, which I don't know if that's a bonus, but we know C enough that we're happy with C written tools, right? And so the way that PG Reorg works, sort of looking at it step by step, and as we're evaluating this, we're trying to figure out how does this thing work, what does it do? So the first thing it does is it's going to create a log table for changes, right? And then after it makes this log table for changes to the table you're trying to shrink, it'll go and put some triggers on the old table and then start keeping track of what's going on, right? Then it creates a new table, copies all your data from the old table into the new table, creates all the indexes you need on the new table, applies all the changes from the log table to the new table. Then it does a modification of the system catalogs to sort of update the information about the table files, and then it drops the old table, right? So there's a number of steps, but if you just lay it out like that, it sounds like it's okay. But the thing that you have to realize is, I said this one thing, which was it modifies the system catalogs information about the table files, right? And so this should be the big scary warning sign, where somebody wrote a tool that went in and basically hacks your system catalogs to sort of change the information that it has about the files on disk. And so the unfortunate part is that as part of our job in sort of making systems scale, we've done bad ideas like this and been very successful with them. So when we saw this, we were like, it was sort of 50-50 within the group. Some of us are like, oh, dude, that's awesome. Like, that's a really good idea. You should hack it that way, and that will make this work. And then the other half said, like, that's a horrible idea. We should never use this tool. This is insane, right? And unfortunately for the guys that were right on the insane side, I was not on that side, and I got to say, no, we're going to do this anyways. And the thing is that what it comes down to, it's not just that I like, running GDB in production as I've been known to do, but if you don't have any other tool to solve your problem, then you've kind of got to use the one that's in front of you. And there is no other tool to solve this heavy bloat in the 24/7 operation environment. So, what other tool are you going to use? You didn't have one, we're using this one, right? But that's a caveat. If you're hacking the source code, that's scary. But PG-reorg, though, it is open source code, right? It's like I said, BSD licensed product. So you can go and look at the source code and see what it does. Another really interesting thing is because it's user space code, the power sort of in your hands as far as being able to see everything that's going on, and when it runs its commands, it runs them as SQL, right? So if you log all the SQL on your system, you can see all the things that it's trying to do. All right, user space tools are definitely very visible. It's a big bonus for that. And so that's one of the aspects that tends to be good for using user space tools. When somebody else makes one, it's very easy to see what it's doing and how it's messing with things, right? So we looked at it, and like I said, we saw attack in the system catalogs, whatever. So then the next thing that you have to kind of do is test this thing out, right? See how it's actually, how it's going to work. And so, the testing, as you can imagine, the first step is really simple. You make some tables, you put some artificial bloat on them, right? Just do a bunch of updates to it, you have some bloat. Then you run PG-reorg, and then you look to see, do I have spaghetti or do I actually have data? And we found, it works. It cleaned up the bloat. We were pretty happy with that. So once that test, right, that's on a test database on somebody's laptop, and you see that it works, and you sort of go through it a few times to figure it out. So then the next thing is sort of tricky, but the next part is you kind of have to go and run this on a system where the data matters, right? So that's what we did, and we're in a unique spot. We have the advantage of we have enough customers where we know which systems are mission critical, and then there's other systems where they are mission critical, but you can kind of play with it, and so we go to those systems when we need to do experimental stuff, and we know they have the right redundancy and that kind of thing to deal with this. So essentially, it's testing and prod, right? But I put prod in quotes because it's the prod that it's okay, if something goes wrong-ish, right? So anyway, so we find some bloated table. We find a database. It's bloated. We make a backup of those tables, of course, because we're not insane. And then you cross your fingers and you run PG-reorg, and it turns out, yay, it does work, right? So now we tested it in sort of high-load environment under stress where things could go wrong and it would blow up. But we also know that we did pick the system where you could go run this, and if it were to blow up, no one would call you right away and say, hey, you're in trouble. So eventually you do have to go and have that run on something that now is really, not just production with quotes, like actual production. So we went to run it on the first sort of production database, OLTP system. And just to give you an idea of this particular one, it's about 540 gigs in size, or was at the time, doing about 2,000 transactions a second in sort of the off-peak downtime of the system, right? And so, again, we're smart. We don't run this during the middle of the day when everything's really busy. We said, Sunday at 4 in the morning, that's when nothing's going on. Let's run it then. But even in that environment, it was still, they're doing a couple thousand transactions a second. The largest table in that system was about 127 gigs before reorg, right? So we go and we set the day up and we tell everyone we're doing it this day and hopefully it's going to work. And so we worked on it for much of that morning, and it was almost 6 hours to rebuild all the tables that we needed to rebuild, right? And PG-reorg works on an individual table basis. So we did the first one, we looked at everything, checked the error logs on the database, make sure everything's still working, and we ended up reclaiming about 52 gigs of disk space, right? And we mostly just concentrated on the tables that had a significant amount of bloat. We thought anyone that had 10 to 20%, it probably wasn't worth it to run the tool, especially because we didn't have the confidence level yet that this thing would actually work. But we got about a 10% shrinking of size, which put us right back into the sweet spot of how much RAM was on this box. So if you do some math there, you can kind of figure that one out. But it got us into a good enough spot where we're like, we used it in a real production system that had it blown up, we would have had some splaining to do. And so everything worked, and we were happy, right? The big one being there were no outages reported anywhere on the website or the APIs or anything. So we're really excited. And we actually went and we have graphs and stuff. And so we use this and, sort of became a regular thing. In this graph, you see these sort of spikes, and that's where PG reorg was rewriting tables behind the scenes, right? And then it drops way down because it throws away the old bloated table, right? So this is good, and we take this success, and now we're sort of bolstered by that. So we run it in some other places, and I'll apologize that I don't have pretty Circonus graphs for this. These are crappy RRD cacti, type graphs. But anyway, so we do this again. Here's another one, right? Somebody else's database we go and run this on. We see the bloat drops down dramatically. Everybody's happy. Also, this takes care of index bloat, right? So here's another one where we run it, and we see index bloat now not so much of an issue. We can make dramatic recoveries there, cleaning that stuff up, and it's much quicker. One command, and so everybody is really happy. We're very excited by this. And we're now using it with a bunch of customers, and we're telling people, oh, we ran it, and on this system there's all these thousands of transactions, and we're really excited. And then let me digress for a second. So there are great philosophers of the past, and I always recommend to think about the great philosophers of the past. There's wisdom there to be learned, right? And this one philosopher, Skywalker, he says something about overconfidence is your weakness, right? And actually, there was a sort of there was a great era of philosophical debate back in the days, where this other philosopher retorted with this idea that faith in your friends is your weakness, right? And so the beauty actually of open source is that with open source you can actually have both of those problems, right? So we had trust in NTT's code, right? That was a faith in our friends. So that was we trusted it, we were running it, was good. And then because we had run it in production and we did it on these large websites with thousands of transactions, right? Well, we're awesome, we're on ETI, yeah. So we had overconfidence that the tool was actually going to work in all scenarios, right? So not heeding the wisdom of the past. We ran it one day, and then we started seeing these weird error messages. And so if you remember, I said I've been working with Postgres for 10 years or more now. And so some days are more interesting than others because there are some days where you get an error message that you've actually never seen before, right? And for me, that doesn't actually happen all that often. I've seen enough error messages in my day that it's a sad thing. But in this case, we got a new one. I was like, hey, this is interesting. It doesn't actually mean anything either when I read it. So, we looked at it, we're like, we knew this was bad because we could see that things were failing, right? We have metrics that are telling us your system is going into the pot, so you might want to fix it. But we see this problem, and we're like, hey, this is bad, right? And so the one guy who's running the PG reorg is like, hello, I got this problem, it's weird. And then as soon as you see this error, you're like, let me go look at that because this is weird. So, we start sort of everyone getting excited or interested about this problem and looking at it. And this was on a production system, right? And they're trying to do thousands of orders a second, right? Not transactions, but actual orders from their customers. And for those that know Kate Matsudiara, if she can't order her Louis Vuittons online, she's not going to be happy, right? So, yeah, orders are failing is generally about as bad as you can get for, what seems to be a simple problem. And it threw us off because if you remember, right, these are warnings inside of Postgres, right? These weren't errors that we were seeing. It was just warnings, but we could see that orders were going down and transactions are starting to fail, right? Such is the life, I guess. Okay, so what was going wrong, right? This is the example that we sort of boiled out as here's how things go horribly, horribly wrong, right? So if you make a little test table like this, right, and so simple table, we have a default on it, and then the way the Postgres internals work is that when it tracks what are the defaults of your table, it doesn't do that based on the names of the columns, right? It does that based on the position of the columns within the table, right? So in this case, that default is based on column number 2, not column B, right? That's how Postgres internals associate that. So what we found was if you drop column A from this table and then you run pg reorg, right? Part of what pg reorg does is it creates a new table based on the columns in the old table. So now the default, though, gets moved. It's still pointing at column number 2, right? It's not pointing at column B. But now column number 2 is actually C, which is a Boolean. So you have this default of 2112 on a Boolean column. And it turns out that doesn't actually work, right? We were thinking about submitting a patch to call this MySQL mode, but we didn't because we had the site down and all that junk. So we had to fix that. And so the thing is, like, now we have this really weird error message, and we're trying to figure out how do you actually fix this, and we're into the system catalogs. It's really bad. And the really unfortunate part is, and I've been reminded by this by several core hackers, is that this is actually fair in the sense that we've hacked the system tables in Postgres with pg reorg to make this thing do what it's doing, right? So all bets are essentially off. There's no real expectation that we should be able to go to someone and say, hey, Postgres is giving me this error. Why did it screw up? Right? Like, it screwed up because you hacked the system tables, so go away. You know, that's going to be the answer, and I think that's a justifiable answer, right? So understanding that, at least we knew what the problem was, and we were able to sort of look at the catalog and say, well, it's all in the catalogs. We can see where the references are pointing. The basic fix that we ended up having to do on this was we dropped all the constraints on the table, and then we recreated them. That was kind of painful. But luckily, they were already losing a lot of money, so the extra pain that we had to inflict to cure the problem, they didn't really notice, right? So that's what we did to fix it. Alternatively, you could have actually hacked the system catalogs more in order to fix this. But the problem is, like, the data types in question are kind of screwy and not like regular data types. It's not like you update some number column and say, hey, that's a 2, make it a 1. Like, it's these weird data types that don't actually work in any place that you'll want them to work except within the core Postgres system catalogs, right? So we could have done that some more, but we already figured, you know, if you think about it, hacking system catalogs more seemed kind of like a bad idea once you're at the stage where I hacked them and I screwed everything up, right? So well, at least for now, like, you know, next year there'll be another talk. There might be another story about hacking the system catalogs. We'll see how that goes. So we were actually able to fix the problem, right, by going in and hacking that. And the problem is, like, you start to cross that line of we made this great user space tool, right? It's running all these SQL commands. It then does this one piece that hacks the system catalogs, and then, you know, it blows everything up. When we got done sort of fixing that problem, we, you know, long summary incident email, like, here's what it was, and here's what the problem is, like, which was the final line of that email was this, right? Like, so that we fixed it, everything's working now, and then, if you'll excuse me, I'm going to go have a heart attack. And definitely, you know, thousands of dollars, probably, you know, potentially millions being lost as this system is chugging along and trying to do its thing, that will lead to stress. So you do kind of have to be careful there, right? So what's next, I guess, right? Once we sort of deduced the problem and we fixed it, as good open source citizens that we try to be on occasion, we did report the problem to the mailing list. Not so much to Postgres mailing list in the sense that we didn't want them to fix it. We talked to the PG reorg mailing list, right, and the NTT guys, and we sort of said, like, here's this, you know, we had the test scenario with the create the table and drop the column, and you'll see this will blow things up. Then one of the guys on the team submitted a patch. He said, you know, there's actually a couple different ways you can fix this. Here's a patch that will sort of solve this, or if nothing else, will prevent other people from stumbling upon this. Because the crazy thing was, right, like, we had actually looked into problems with drop columns before, and we just hadn't seen this problem, you know, after even months of using this in these heavy workload systems. So it just so happened that finally we hit the right combo. If the dropped column is, you know, if I dropped C in that test table instead of A, like, you wouldn't ever see this problem, right? Because you haven't shifted things around to get into that trouble. Ultimately, that problem is actually fixed. This is fixed in PG reorg now. Like, if you were to hit this scenario, you wouldn't actually have this problem, right? So everyone's happy, essentially, I guess. At least we understand the tool a little bit better, and you know, we're back and using it. We did actually, there's been discussion on the Postgres side, you know, about the bloat problem and sort of a resurfacing, right? And I would say that the Postgres development community kind of can be funny, not in a ha-ha way, but in a strange oddness way. You know, it's sometimes hard to get them to recognize problems that are out there in the field, I guess, as I like to look at it, right? And it's one of the aspects, like, I noticed this a long time ago, is that actually, if you're a core Postgres developer, chances are what you do is you sit in a room all day and you write C code writing the database software, right? You don't actually go run the database software anywhere, right? And so, you know, in fairness, like if I'm writing code, like that's probably what I would focus on most of the time. And so getting people to recognize, hey, this is a problem, we need to solve it, you know, it's tricky. Not everyone sees the online rebuild thing as a big problem, right? I think it's a big problem, but that's probably because I have this problem, right? Not everybody does. So if you don't have this problem, if you're not getting bloat in your system, you don't think it's a big deal. Going back to that idea that every non-overriding storage system is going to eventually have this problem, you know, it takes a while for a community to get to the point where you have enough stuff going on that you have to find better and better ways to deal with this, right? The first, you know, I'm sure the first, you know, N months of MongoDB life, dumping all your data out of Mongo and sticking it in a new instance to compact things was actually an okay solution, right? Nobody was putting a lot of data in there. But as you see those data sets start to grow, like that's the kind of thing you're going to run into, right, using these different projects. And so, you know, we've had the discussion in the Postgres world about this. At the hackers meeting, which was in May of this year, there was a discussion on building like an internal queuing system inside of Postgres. And if you were to have that, I think you could actually use that as an underlying basis to do the online table rewriting from the Postgres side, right? So it'd be like sort of take the PG reorg tool and recreate what it does inside of Postgres core, right? And so, you know, whether that's actually going to happen, I don't know. The queuing stuff seems to be backlogged, and that wasn't actually the original intent of it. That's sort of my thinking, hey, if we did have that, we could work on these tools. This is actually something that we find that we have to do, you know, often enough, I guess, is that you'll look at a particular project and you'll find some deficiency and you build a tool, sometimes I think only just to prove, you know, sometimes to solve your immediate problem. That is a good goal. But the other thing is if you can get enough people using the user space tool, then it becomes sort of a legitimized need, right, that the core product actually ought to have this because everyone's using this workaround. And so, you know, you'd probably prefer that the core product just would like make it for you the right way the first time. But I've sort of given up that dream in my life that that's always going to happen, right? Sometimes you're going to have to write some code yourself. So that's fine. I would say PG reorg is a great tool. If you have, you know, high transaction and you're using Postgres, you at least need to be aware of it because at some point you're probably going to run into this problem, right? And you're going to have to figure out a way to deal with this. It is the best option in a difficult situation, right? So look for user space tools in that sense. Don't be afraid to use them, right? I would say test them and understand how they're going to work because, like I said, you know, in this case, this did sort of bite us this one time, even after months of using it. So being able to go in and look at that code was definitely helpful. Did who? Yeah, so I think they didn't actually use the patch like verbatim, but they put in a fix into the newest release. Like I said, so just be careful, right? Like use the user space tools, build your own if you have to, and be careful about them. So, Clinton says I got 5 minutes for questions. Yes. So auto vacuum is basically a daemon process inside of Postgres that runs the vacuums for you automatically. The cases that we've seen, it's not any better, right? It has the same deficiencies that vacuum has. It can only run so often, and especially if you have a lot of tables that are getting updated frequently, right? It has to spend its time doing a lot of things, and it's limited to the number of times it can run a vacuum based on settings of the auto vacuum daemon. So we're big fans of auto vacuum. Like I was really happy that got into Postgres. And we use it, and I think that covers, you know, actually the default settings of auto vacuum solve probably 75% of everybody's problems. If you tweak them slightly, then I think it goes up to 95%. But the problem is there's still that other 5%, right? And maybe we live there more than other people, but I think one of the other things is that because we're, you know, kind of monitor-driven organization, we wrote tools to go and figure out when this is a problem, right? We run those bloat reports on systems just sort of as a matter of course. Like setting up monitoring, part of that means, you know, setting up something to run the bloat report. So it's possible, I think, that a lot of people have bloat and they're just not aware of it, right? And if they were to run a bloat report, they would see that that's an issue. Sometimes it cleans itself up. Depending on the size of your system, you might be bloated, but if your upgrade process involves, I get 1 day during the year where I can do an upgrade, and we do a dump and restore from the old version of Postgres into the new one, if you're still following that model, maybe you're cleaning up the bloat, once a year, and that's enough for your particular workload, right? So a big fan of auto vacuum, we definitely use it. There are some places where we've had to curtail its use. If there are really peak times where you're stressing the I/O load, so maybe you turn auto vacuum off, for 2 hours or 4 hours or whatever that window is, right? In those cases, then you really start to see the bloat creeping into things, right? Because you have a strategy that's only working 20 hours out of the day, and it might do a good job then, but that other 4 hours, you're going to kind of bloat things out. So it's a great thing. You should definitely be using it, but I think you can still end up seeing bloat inside your systems. It depends on the ones that are bloated. I guess I would put it that way. So, and actually the interesting thing about PG reorg, because it's all user space commands, right, if you just turn full logging on your database and you run those commands against any table, right, you now have all the SQL that you would need to run this on anything, right? The only one that gets tricky is, I think PG class is tricky because it has to update the actual file pointers inside of PG class. So that would be tricky. You might be able to do it in standalone mode. But I guess if you've gone into standalone mode, then maybe you should just vacuum full it, right, like at that point, hopefully. Even I'm not that much of a glutton for punishment, so. Any other questions? No? Okay. Thanks much.